Okay, so I also share myself.
Yes, okay, very good. So I will introduce you, and so just so that I don't make a mistake, are you a professor of physics in the chemistry department or professor of chemistry?
I don't know.
You're just a
So
professor, okay.
I'm a professor, yes.
We'll leave it at that.
Yeah.
By the way, can we let all the participants to open their camera for snapshot? We still do not have enough participants now. I think it should be the order of 100. Yeah.
You're getting greedy here.
Yeah. No. I just remind that there is a snapshot section. Yeah. Yeah.
So Jiangyong will record your talk if it's okay with you.
Yeah, I'm totally fine. So, okay, so my Spotify just start to play, so I had to close it. So I was, gave me a lot of, so I had to stop sharing. I don't know how to switch screen. So, okay. All right. These days, there are so many online seminars, and it took me a while to find the correct email because the links are all different. And
yeah. It's the new way of sharing.
yeah. I don't know about other people's experience, but the last few months actually quite interesting. There are so many information online. Actually, it's a good time to learn stuff.
Yes.
I really like the stuff I've been recorded because like if you want to share something, discuss with students in the past, it's actually very difficult to find videos that on our field, right? None of the student lectures in the Quark Method were recorded. So you have to explain the talks to them. And I like the new way, you just listen to the seminar and discuss as, student raise questions. It's actually the recording is quite useful, I would say.
That's why we're doing it, yes.
Yeah.
All right, it's 10 a.m. On the East Coast. I will wait for another minute, then I will start to introduce the speaker.
See, we have 100 people now. Should we ask the people to open the camera and take a snapshot first?
Yeah, do that. So everybody, please open their cameras. After we start the talk, please close them again. But we will now take us a few snapshots to put on the website to document the outrageous interest in this field by the community. So we have 105 participants and the number is still climbing. 107, 108. Okay, once again, please open your cameras for a few minutes so that we can take a family photograph of the BES family. While we are doing that, let me introduce today's speaker. We are very happy to have Jiangyong Jia from Stony Brook University, professor from Stony Brook University, as our speaker today. This is the third seminar, I think, in a series that we started because a workshop that was dedicated to this subject got cancelled, had to be cancelled because of COVID and travel restrictions. So we are trying out the new way of disseminating and discussing science. while Jiangyong is giving his talk, which will be recorded and also posted on the website afterwards, we will collect your questions in the chat. If you have questions, please put them in the chat. I and Hui Chao will monitor the chat, and questions that we believe should be immediately answered by the speaker will interrupt Jiangyong to do that. And the others we will collect for the discussion series at the end, the discussion time at the end of the talk. So, Hui Chao, do you think we have had enough chance for photographs?
I'm trying to. It's kind of okay. Xiaofeng, are you okay for the photograph? Or Baochi, are you okay with the photograph?
I actually have taken some of them and I also sent to you on the WeChat. You may take a look.
Okay. Okay, maybe I think it's kind of okay. Yeah.
Okay.
All right. So then maybe you can close your videos, and except for Jiangyong, who I think you would like to continue speaking, and I will start the recording, and we are ready to go. Jiangyong.
Okay. I would like to thank the organizers to invite me to give this talk, which of course it did not happen in person, but I'm really honored actually to be able to speak and tell you about my personal opinion on the flow studies. So my talk actually have just 3 parts. I will start with a short, very short introduction on the flow phenomena, and then I discuss the challenges in the current studies, and also give you my personal opinion on what some of the opportunities are. So I think the one of the main challenge in the flow study, although actually flow is a dominating phenomena of the heavy-ion collision, right? So this is the first thing you see when you study the heavy-ion collision. You know, this is the most dramatic thing that happens in heavy-ion collision. So the system behave collectively. But nevertheless, in order to go to the details, there are still challenges. The main issue is that we need to determine both the dynamics and the properties at the same time. And we know the properties, of course, it drives the dynamics of the system. But in order to extract the properties, you need to be able to really know what's going on with the dynamics. So this is the challenge. And the way we do it is that for any dynamical system, you basically try to perturb the system, right? And see what happens to the system. So the way we perturb this system is to use different initial conditions, fluctuating initial conditions, different energies, different collision system, and we perturb the system and see what happens in the final state, and then we use the models to relate these two. So in fact, the fluctuation initial state is very strong. What you see here is the event by event simulation of the particle density distribution in the phi and the eta. And you see this is a single event, and you see the pattern is already non-trivial. There are structures in the phi and the eta direction, and it fluctuates event to event. It's very different pattern if you change the event, the initial state. Now there's also structures within a single event. One often write the particle distribution in terms of the Fourier series, but the coefficient, the amplitude of the flow and also the phase of the flow are differential quantities. It in principle also depends on the pseudo rapidity and the transverse momentum. Now, how do we study this object? In the single particle distribution, the probability density function of the flow, one can actually expand in this simple form, where you have the coefficient I wrote in the earlier slides, plus this normalization factor, which could also be a function of PT and pseudo rapidity. And one can write this in this compact vector form to encode the phase amplitude. But I want to point out the leading term, I mean, the most important term in this expansion actually is the radial flow term, the normalization term. Then one can construct correlations from this, right? Because we only see a finite number of particles in each event, so you cannot measure the first, the single particle distribution event by event. Instead, you average over pairs and triplets and quadruplets and so on and so forth. And this average will of course encode the information not from a single event, but it's actually also encoding information from an ensemble distribution. So it's can be quite complex. If you do that, you will see for the two particle correlation, for example, you get this, the quantity you can measure is the Vn times Vn complex conjugate. This is the two particle flow harmonics. And you can also do in the multi-particle correlations, the quantity you extract have to appear in this form. They have to be global rotational invariant. So that means in general, the quantity you measure carries information about the flow amplitude and also the phases. And depending on the choice of the flow harmonics, the phase actually can totally drop out. Basically, all the angles add up to 0, then you get a pure amplitude fluctuations. So if you look this expansion, you actually can see immediately that this simply is a Fourier coefficient of a joint probability distribution of all the Vn's and all the phi n's. And this is the event by event quantity, the general object you could measure. And these correlators are just one of the Fourier coefficient of this object. Obviously, there are many of them. If you look at the single flow harmonics, we have measured for n from 1 to 7, with different orders and up to 8 particle correlations. And this is the single flow harmonics. And we also measure the correlations between two different harmonics, so-called the symmetric cumulants. And we also measure those that contains the phase. It's the event plane correlator. So some people call it asymmetric cumulants. And there's also correlators involves the V0 term, the radial flow term. So you can write down the correlations between the Vn and the mean PT fluctuations, or simply the mean PT correlations themselves. So I counted there are at least 50 different observables has been measured. There are a lot of them has been measured. So that's why we have a lot of, this is a rich field, and we have so many theoretical work going on to try to utilize this data. Hello, can you hear me?
Yes.
Okay, so somehow went to, I need to find my mouse, sorry. Yes, I don't know what happens. Let me reshare.
Okay.
Oh, no, sorry. This never happened before to me, so I don't know.
Okay. While we are doing this, I made a mistake and made Wat Zheng host rather than Hui Chao. Wat Zheng, are you there? Can you open your mic?
Let me rejoin. Sorry about this.
Yes, I'm here. I will try to pass the host to Hui Chao.
Please. Very good, thank you. All right, Jiangyong, now you have to unmute your mic again.
Okay, can you see my screen?
Yes, but if you make it full screen, yes.
Yeah.
Okay, I think we are in business. Let me restart the recording. Okay.
Okay, sorry for this accident. Okay, so I just continue. So the data actually allow us to do in the early days to do a precision comparison constraint on the models, which over the years improve the precisions of the transport properties. And so we were basically, extracting one parameter at a time, or maybe a couple of parameters at a time. And since about 2014, there's actually a lot of effort goes into a multi-parameter, this adaptive fitting procedure to really try to optimize the constraining power of the data, and a bit within a given model, right? So there are still model alternatives, but this at least give us a differential information in the high dimensional parameter space. And here, just one example shows you that we can extract the shear viscosity as function of temperatures, and we can actually constrain the functional form and also give an error band which depends on the temperature. Just one example. So at this moment, this multi-parameter, this fitting only utilize a limited set of observables. And for example, the one I showed you only uses the spectral MPT fluctuation, the Vn harmonics. This is the two-particle harmonics. The reason we didn't go, use all the observables is because of number one, this simulation is very computational expensive, and you need different observables obviously require different statistics, and it's very hard to generate large statistics. So unless in the future, if we can solve this problem, this will be one of the bottleneck, is that have a fast and efficient simulation, just like what people do in the experiment. We do a fast simulation that go around this Jiangyong simulation step, right? So this will be something that is that we need to look into. But the other issue is that the models itself still have a lot of parameters, and so there are many things you could still change in the assumption that goes into the models. But in principle, if we look at these high order flow fluctuations, they could provide very strong constraints on the models. The only question is that at this moment, the models with their current input parameters, they are already being over-constrained by the observable they used to do the fit. So adding additional observables may not really improve it, because there's already tensions between describing different observables. But in principle, in the future, we need to be able to include all these measurements. This then concluded my introduction to the flow. Let me continue the discussion in the context of discussing the challenges for improving our understanding of the heavy-ion collisions. One of the we all agree that we don't have a ab initio QSD theory, implementation of the theory that allows us to do a first principle calculation. So therefore, we often artificially divide the heavy ion space-time dynamics into different steps. And each step comes in with its own assumptions and parameters. And so we have this initial state, which obviously have initial geometry, and it also carries the initial momentum anisotropy, and then the system undergo a very rapid thermalization process, and entropy are being produced, and then later evolution could be described by hydrodynamics with a whole set of different parameters like shear viscosity, bulk viscosity, equation state, and also non-equilibrium dynamics. For example, if you talk about QST critical point. And then we have a phase transition, hadronization, and hadronic transport and freeze-out, which I do not actually discuss in this talk. So in the theory, what you could do is that you fixed, all the stages, right? You fix all the parameters except one phase. You can, for example, just focus on the initial state. You fix everything else. You vary the initial state parameters, and you study the sensitivity. But this is hard to do experimentally, right? You would love to be able to do a controlled experiment experimentally, and this will give you direct constraint on these parameters. But unfortunately, this is hard to do. But nevertheless, this is something we try to emulate, right? Whenever we do energy scan, we do a system scan, that's the ultimate goal, is to be able to fix many parameters and vary only a limited set. And so this is still, of course, is challenging, but this is what we aim for. Let me discuss this. Follow the following slides. Just focus on these different ingredients of this picture. I'm going to discuss different stages. Start with the initial state. This initial state is by far the most important phase, because it provided the most important fluctuations, which we use to define the hydrodynamic response. We know there's a linear response works pretty well on average for the first few flow harmonics, and this has been measured up by, actually confirmed experimentally by this scaling plot for different system and different energies. And in the small system, there's a large uncertainty, obviously, because our knowledge of the scaling is limited by our knowledge of the initial eccentricity, right? So there's still more uncertainties, but nevertheless, these results are largely consistent with a geometry-driven hydrodynamic response. But if you look at this data more carefully, or the hydro calculation more carefully, you see that even for events in the narrow centrality class, there's still like a quite large spread between the Vn and the epsilon n. And this spread, I think it contains very interesting physics, and it can be quantified by this Pearson correlator coefficient to quantify the departure from this linear relation. You see there's this deviation actually is quite large. Well, it's there for all centralities, but it's become larger as you go towards more peripheral collisions. And my question is do we actually understand the origin of these spreads, right? So people did some work in the last few years, try to understand this. For example, we know that the leading eccentricity should not capture all the information about the initial state, because eccentricity is a single number, but the initial geometry is a two-dimensional information, right? You have you do not only have the azimuthal angle, but also the radial direction. So in fact, you should consider the subleading eccentricities that arises from the radial modulation in the initial state. Here, I just show you a plot from the paper from Directini and Alexis, shows that if you look the initial state event by event, if you look the triangular shape, that is coming from this fluctuating participant nucleons, you will see that not only this fluctuation should give you this leading eccentricity, look like a triangular eccentricity, but it should have some radial structure, right? So overall it's still epsilon 3, but it's actually this epsilon 3 depends on the radial coordinate, right? It's a kind of flip sign. So this lead to the subleading flow, and this subleading flow basically have a node in the PT, they intersect cross 0, and the more high order, the more crossing point you will have. And this lead to a breaking of the fractalization of the two-particle flow harmonics, for example. This is an important insight. And one could try to resum all these subleading contribution, and also in addition include the model mixing term to see whether you can explain the spread between the epsilon n and the Vn. It turns out this, including all these high order eccentricities, and only in the linear response framework, you could improve the, reduces the spread, but still there are stuff still remains, okay? So you can never exhaust all these residual differences. And so I think we still need to really understand what kind of, maybe this is the, in considering the initial state is not enough, right? There may be some dynamical fluctuations which are important, and we need to systematically separate and understand these different contributions. So another way to look this difference is to just directly look in the high order flow fluctuations. For example, looking into 4-particle, 6 and 8-particle correlations. If you have a linear response, you may argue that the Vn, the cumulative ratio should be given by the eccentricity ratio. And we already know this doesn't work, because in the hydro calculation, you see that the eccentricity ratio is different from the flow ratio, right? Even in the hydro, you see it's different. And this difference depends on the centrality. Experimentally, we also know, we actually have seen this, right? So the V4 to the V2 ratio is not the same if you change the PT ranges, right? And you can see there's a clear PT dependence where the fluctuation for V4, I would say increases as you go to higher PT. And so for V2 it increases, for V3 also increases, but because of the average geometry component contribution to the V2, you will see the opposite direction. So one goes down, the other goes up. And so this is direct experimental evidence for this breaking of the linear response. And so the reason, the question will be, what caused this, right? Maybe there are some initial non-equilibrium dynamics, like initial momentum anisotropy, or initial flow, or maybe the dynamically generated final state fluctuation that lead to this PT dependence. And I think it's interesting to study this further. We can also go to small system, and we know in the last quark matter this was reported. We saw that the 4-particle cumulant from a pure hydrodynamics calculation, which only consider the initial geometry without, the initial flow and the other effect, that the sign of the C24 is opposite to what the data shows you, right? So you get only a positive C24. This was argued is probably at least partially due to the appearance of the cubic response for the V2 in the PP system, which is particularly large when you go to PP collisions. And you may, one may just need to look this 2-dimensional correlation and really understand what's going on, maybe do some kind of event shape engineering, really understand what is missing. Because if you cannot, the hydro cannot describe the data, well, we need to understand what is missing, okay? So since I'm discussing the small system, I'm going to move on to the role of the initial momentum anisotropy. We know in the small system, it's very important in order for the hydrodynamics model to work, you need to put in the enough subnucleonic fluctuations. You need to have enough fluctuation to generate enough eccentricity and connected sources, right? They should not be separate from each other in order to generate sizable final state flow. And this is really required in order to describe the flow in the hydrodynamics model framework. But on the other hand, it's also natural to expect initial momentum anisotropy should also contribute, right? So in this calculation, you can see this contribution in the P-led system could already be quite large without consider the final state effect. One can do a more systematic study where one include contributions from the momentum and stress component of the initial energy momentum tensor, which are the sources for initial flow. You can see that as you change the system size at the rig, this is the rig energy, you see the correlations between this Pearson correlation between the eccentricity and the final state of flow, and also the momentum anisotropy versus the final state flow. You see this correlation goes in the opposite direction. So that means in the very small system, even in the central P-led or central D-gold collision, you may have a large contribution that is uncorrelated with the initial eccentricity that is only given if you would only consider the energy component of the T mu mu. So, but my question will be, do we actually have any direct experimental evidence for this, right? So I would say this is the indirect, it's the way how you interpret the data. But do we have something that just you look at it, you can directly associate it with this this interpretation? I think this is I would like to see this direct evidence. Talking about the initial flow, this actually is naturally required, right? Because we always ask the question, you know, what is the why the system reaches local equilibrium so fast, right? So that means, you know, for example, in the study of this bottom-up summarization process, we have to introduce interactions, final state interactions that dampens this momentum anisotropy, because you need to damp them in order to, you know, to match smoothly to the hydrodynamics. You need to actually, which are important to drive this QGP, right, towards local equilibrium. And more importantly, you need this phase in order to produce entropy, because in the hydro phase, you do not produce enough entropy. So this is just this effect must be there, right? So the question is, how do we search for this? This non-equilibrium effect experimentally. We know they are important for the Wien and the PT spectra at the intermediate PT. This is the no man's land, right, for the hydrodynamics and jack quenching studies. But these regions, we all know, is very important. It captures all these non-equilibrium dynamics. How do we identify and quantify this effect? And then maybe try to extrapolate this, extrapolate from this intermediate PT to lower PT, and try to understand what is their role for the bulk physics. And so I think this is one of the remaining direction that many people are focusing on and try to basically gain insight about. And then let me move on to the next phase, and also then discuss maybe just discuss the question is, do we actually reach the hydrodynamics dynamic model phase, right? So this is the question that may depend on the size of the system. So people argue that maybe in the small systems, the number of scattering may not be enough to reach this hydrodynamics dynamics phase. So instead of having this pressure-driven anisotropy, final state anisotropy, one may think that the system is not in local thermal equilibrium, but instead what you see is that is the surface emission picture, or people call it anisotropic escape or anisotropic absorption picture. They both reflects to some extent the final state geometry response, because you have this relation between Vn and epsilon n, but these imply a very different space-time dynamics. Okay, so the one way to think about it is that in this recent calculation, which imposed this transport model, you can see that when the number of scattering is small, the response coefficient should also be smaller than the hydro limit. So maybe this is the one way to identify whether we are how close we are to the hydrodynamics picture. But I think the challenge still is that in the small system, we do not know how to calculate the eccentricity reliably, right? We need to really quantify the uncertainty there. So maybe one should, instead of doing this, one should also try to search for signatures in the data that directly support this physical picture versus this physical picture, right? So in the first case, when you have a hydrodynamics picture, the particles should, their momentum distribution is should follow a single body distribution, right? Because this is given by the T mu mu. You don't need the concept of particles. You only have the energy momentum flow, which basically should not have any short range structures. You only have these correlations between the final state flow of the fluid, which are correlated to each other simply because they see the same eccentricity. By the way, I'm plotting the rapidity. This is the rapidity direction. If you look the transport picture, the way you generate the flow is through the final state scattering. And this scattering will have to give rise to short range correlations. And the nature of this transport theory, transport mechanism, right, should be reflected by the properties of these short range correlations. In other words, if you only look at the long range, what you see is the geometry response. You will not be able to really tell directly whether it's hydro or transport, right? You just cannot tell because they all responding to some common geometry. We should actually probably go back to look the short range correlation. This will tell you the microscopic scattering mechanism. But of course, this is challenging, we know, because this is sort of like a collector of all kinds of physics, like including the resonance decay and stuff like that. This, I would say, this is still our one of the area, or our, in my opinion, is the best hope to really understand what is the macroscopic mechanism for the development of the flow. Okay. So let me move on to the longitudinal direction. We know the initial condition of in the Havian calculations it changes with rapidity in a single event, right? So in this, we know that we really don't have a boost invariant system. Maybe it's very close to a boost invariant in the high energy, but in principle, the geometry of the initial state depends on the rapidity due to the forward-backward fluctuations in the initial state. This can also naturally arises from just simply the gene walk evolution in the CGC picture. If you take this picture, you would naturally expect that the initial space-time fluctuation should translate into the final state rapidity fluctuation in the flow harmonics. And the same thing is true for the first order. If you talk about the radial flow or talk about the multiplicity fluctuation, there should be a quite large decorrelation effect as well. Experimentally, this has been measured in both the RIC and top energy of the star. Somebody want to make a comment?
And everybody, please close their mic.
So, thanks, Uli. So we see that the decorrelation measured using this three beam correlation, we see that we do see a small but significant decorrelations, and these decorrelations have a non-trivial energy dependence because we already scaled out the beam rapidity, and we see some residual differences, right? So you cannot assume simply a boost environment picture or just simply boost the scaling picture to simply take out all these physics. There are actually interesting dynamics going on in the rapidity direction, and these are not yet fully described by models. And we also see these physics are sensitive to also the final state effect, in particular the thermal fluctuation and the stopping mechanism. This has also been, the decorrelation has been also measured for different collision systems, in particular compared between the xenon and the lead. This is a complicated picture. I'm not going to attempt to describe it fully, but just show you, just focus on the red data points. This is the strength of the decorrelation compared between the xenon and the lead. And the blue is the strength of the ratio for the single flow, right? For the VN, inclusive VN. And you see they follow very different centrality dependence. And you can plot this quantity using different x-axis. You can use a centrality, maybe the best way to use n part over 2a basically is simply a centrality measure, or you can use n part. What you see is that they follow each other much more closely if you plot it as function n part over 2a, and the simple initial state model can describe it. This means this system size dependence of the decorrelation. This mainly reflects the overall shape, not the size of the system, right? And you can imagine this quite naturally that the amount of decorrelation between forward and backward is driven by simply, if you know, what you would say is that you have the shape of the overlap region and the contribution of the projectile versus target in this overlap region. And that's only, the shape is probably if you scale all the system of different size, they probably, if they will follow roughly the same kind of initial state decorrelation. We also, in some model study, people have shown that these decorrelation are also sensitive to nuclear deformation effect. And currently the models, the hydro models need to improve their statistical uncertainty in order to really gain some more detailed understanding on this. But I think this is a promising direction. And one can actually break the boost invariance further by going into the beam energy scan. In the low energies, we know this the new nuclear overlap time become much more important, right? So this is the picture for top RIC energy, and this is a picture for 19.6 GeV. So you can see this overlap time is quite significant. So the nucleons will be decelerated and deposit their energy over a much bigger space-time volume. And so this picture we had before, where we separate the physics into different phases, no longer work. And so that means the system is intrinsically is a 3+1D. You cannot ignore the longitudinal dynamics and only model the transverse, which we could do at the top energy, but at lower energy, you cannot do that. And the overlap between the, for example, the longitudinal stopping process and transverse expansion, they happens at the same time. And the flow itself, you cannot expect, it only reflects the single eccentricity, which only describe the XY, right? Only the transverse shape of the geometry. And so there are other interesting phenomena happens. For example, the appearance of the global vorticity. I mean, this is important. Obviously, the medium itself have a different transport properties, right? So it's an intrinsically different medium. The hadronic phase will obviously become much more important. So this really is a challenge to model them correctly, especially in the lack of sophisticated flow measurement, which we do have some, but it's not really, compared to top energy, we don't have as many. All of this will be a challenge for the models to really improve in order to get narrow down the uncertainties. So let me just flash a few measurements in this area. We know there's a measured, we have measured the V1, which are mainly reflecting the sideward deflection of the spectators and also the produced matter. This actually is very sensitive to the equation of state, right? So it's very sensitive to the how much deflection you have, therefore is sensitive to the equation of state. And we have measured the elliptic flow, and the flow started at the very low energy is a bounce off because you actually do not produce much matter in the middle. And then at a few GeV in central mass, you start with this squeeze out picture because of the passing time is still quite long. So the produced matter can only go out of plane. And then you go to the top energy, you start to have this pressure-driven in-plane flow. And this is really shows you there's a very interesting longitudinal dynamics as you change the beam energy. Recently, there are also efforts to measure the high order flows. And here is a measurement by Hadi's experiment. I really find this plot really, really interesting. You can see that in the forward rapidity, the overall shape of the fireball, if you do event average, is a triangular shape, but it's shifted, right? So that means you have a large V1 and a large V3. And in the mid rapidity, is mostly V2 shape. And they actually analyze this as function of PT and function of rapidity for different species, proton, deuteron, and triton. I'm not going to discuss the PT dependence. I'm going to just look at the rapidity dependence. What you see is that all the harmonics is rapidity odd, and all the even harmonics is rapidity even. You actually can see the squeeze out effect and maybe the bounce off effect, right? This is really also probably depends on the rapidity, whether which region you are. So this is a very interesting result. And all of this so far has been measured relative to the first order event plane. If you can measure high order flow harmonics in the first order event plane, this already implies there's a very large mode coupling effect, right? Would be interesting actually to measure them relative to their own event plane and as a comparison, and also try to measure the event by event fluctuations. Given the fact that you have a large, very good event plane resolution, which means you have a very large signal, this may be possible. Okay, but currently it's a challenge to the theory. They showed this result, but they also lamented that there's no models yet that they can use to do the comparison. So for my remaining 15 minutes, I'm going to discuss a little bit about the future. Again, this is a heavily opinionated talk. So you may fill in the discussion session on this. I think for the top energies, our approach should be still continue to aim for further improvement on the precision of the dynamics and the properties of our measurement and the modeling. This is because it's easy to do because we have a larger multiplicity, right? And the system is roughly Bose invariant. So it's easier for both experiment and the theory to tune the model. Once we have we tune this model very well, we have a good understanding on this baseline, then we can proceed to actually model the beam energy scan. And there, I think there will be quite a lot of challenge, but I think this is where the opportunities are. We should try to identify observables that, there are many observables we haven't measured, right? We will see whether these provide some direct physics intuition on the dynamics. And we should really do more measurement on the flow fluctuations. And with the STAR ITPC upgrade and the EPT upgrade, so this should be possible. With all this, we should then aim to improve our understanding on this different component of the space-time dynamics, which I'm going to discuss, give you a few examples. And then there's also in the future direction, we can focus on the collision energy dependence and the rapidity dependence. Let me start with this puzzle in the ultra-central collisions. In the early days, around 2010, and already we saw that in the ultra-central collisions, there's this peculiar ordering of the flow harmonics. V2 is equal or maybe even smaller than V3. But in any model, global model calculation, you will see that epsilon2 and epsilon3 are roughly equal. And so this is counterintuitive because you would expect there's more viscous damping for V3, right? So this order is hard to understand. Over the years, there has been a lot of effort try to understand this. They have tried to use the final state physics, tuning the final state parameters to see whether you can describe it. Or they tried also many different initial state physics. None of this actually is sufficient or at least it's not, I would say, convincingly demonstrate that they could explain this. And this remains to be a puzzle. And one thing we haven't looked in more detail is to include the longitudinal dynamics into this game, right? Because if you look at the flow decorrelation data, the V2 have this very peculiar shape in their factorization breaking pattern in the rapidity, right? So it's a quadratic dependence, and it's very large. It's like up to 10%. So if you look at the initial collision geometry, you will see that the energy deposition coming from the projectile and the target, they actually can fluctuate independently because there's no constraint on their shape. And even the center of gravity can be shifted from each other. They could actually cancel each other, right, in principle. So there's very large fluctuations. I think maybe we should look into the subleading flows, the PCE analysis with the subleading flow, but also doing this simultaneously in both the longitudinal and the transverse direction to really dissect this physics further. Maybe we can learn something. And recently there are also interest on study the correlation between flow and the radial flow, because the radial flow we know is anti-correlated with the size of the system, right? The smaller system will give you a larger MPT, for example. And since the size is correlated with the shape, that means the V and the PT are correlated. And so there has been measurement by Atlas to show this, all right? So you have an interesting centrality dependence of this correlation. They are largely positive, but then there's a negative correlation in the peripheral, which is actually quite non-trivial. And also this interesting behavior in the ultracentral region. And then STAR actually did a first preliminary measurement also in different system like uranium versus gold. What you see is that actually in the central collision, the V2 PT correlation have anti-correlation. It's anti-correlated in the uranium, and it's positive correlated in the gold. This is an indication of the nuclear deformation effect because it have a non-trivial contribution to the correlation between the shape and the size. And in fact, if you look at the recent model calculation, you can see that it can capture approximately this shape size correlation in lead. And there's also predictions on the effect of the nuclear deformation. You can see if you crank up the deformation uranium, you can actually create deformation, negative correlation. So that means the data can be used to study the initial state effect. So I would like also go back to this early time dynamics, okay? So one of the important point is that we, in the small system especially, we don't know the contribution from initial state and pre-equilibrium versus the hydrodynamics. And we have done like extensive energy, the system scan, but we haven't done, this is the asymmetric collision system, but we haven't done a scan of the symmetric small systems. Anywhere between the PP and the copper-copper collision, we really have the ability to do, but haven't done it. And I think this is important for us to provide the level arm that can disentangle these different contributions. And why we want to do the small system, small symmetric systems? We know, for example, if you collide the asymmetric system, the initial state is very hard to constrain, right? Because the role of the subnucleons, fluctuations dominates, is very important. But it's hard to calculate this or model this using first principle calculations. But if we choose a small symmetric system where we could actually dial the relative importance of the nucleon degrees of freedom versus subnucleon degrees of freedom, we actually can bridge the result from P gold and gold gold, right? Have a bridging these two contributions. And we could start with oxygen, because oxygen have a n-part coverage that covers very well the P gold and D gold system, for which we still have this ongoing debate of what's the nature of the initial state. And with oxygen, since we introduced average geometry, you can already see the influence of the average geometry. So this will give you a sense of how much importance of coming from final state, and then versus the fluctuation-driven component which is for V3, and which will be probably more sensitive to the initial state, but of course also final state. The point is that you have the lever arm to entangle these two different contributions, and STAR actually is pushing for this short oxygen run in 2021. We actually need the community support to make this happen. Because this also have a nice synergy with the LHC oxygen run. This will be very interesting because this will be a 7 TeV oxygen collision, which have the same global geometry compared to STAR, but will be totally different subnucleon Nick fluctuation. So this is another way to change the initial state and observe what happens in the final state. Continue this line of argument. We know that the beam energy scan program has been vastly successful, right? We explore the QCD phase diagram. We bridge between the high T and high mu B frontier. I think an extensive system size scan could also be fruitful. The reason is that this provides a way to explore the initial state, to really detailed explanation of the initial state. And actually, understanding of this will also improve our understanding of the hydrodynamics. And this actually bridge also with another community, which is the nuclear structure physics, right? We can do this VN flow correlation, flow PT correlation, PT correlations, for example, to learn something new. So I already showed you this. I gave you 3 examples. The first one is nuclear deformation, which I already discussed. But actually, if you look this map of the Z versus N, you see there's a large number of nuclei with very large deformation. Is comparable even with the uranium. And so if you think you understand hydrodynamics, then you should be able to measure this deformation and confirm or compare with this table, right? So this will be a way to show that you really control the hydrodynamics, but of course, it's also a different way of measuring the deformation effect. We're not relying on the EM's transition, but we're actually using the heavy ion collision, this multi-particle imaging to directly see the deformation effect. And another direction has been proposed is alpha clustering effect, right? So we can consider colliding the carbon, which people hypothesis is due to is a 3 alpha clusters colliding with a large nuclei. So we can image the shape. If you collide a flat on versus the sideway, you see you produce different multiplicity, different triangularity, and different ellipticity. You should see they have a, as function of centrality, the fluctuation of the epsilon 2 and epsilon 3 will be different. You should be able to use this information to analyze this initial state and extend it into maybe oxygen as well, and also this beryllium, according to this paper. One could also use ability of the rig. You know, the rig can really do a lot of I would say, a novel way of doing the nuclear physics. For example, you can actually collide the ruthenium and the zirconium, alternating the days, right? You can alternating the 2 species, so you can minimize the systematic uncertainty from the detector and from the accelerator. And so you can actually use that to constrain the initial nuclear geometry. And we know that, for example, the neutron string effect between these 2 isobar will produce different profile in the radial direction. And this will lead to, for example, a simple prediction that, for example, the multiplicity distribution will be slightly different. But if you can control the systematics, which we believe you can using this unique way of a rig operation, you'll probably be able to measure this and constrain this initial condition, and also on the eccentricity difference. And that will be a new way to study the neutron, nuclear structure physics. Maybe use it to constrain, for example, even the symmetry energy. And this should be doable in the next few years. So I'm a little bit over time, but I have 3 slides left. So I hope the chairman allow me to finish. Let me move on to the rapidity direction. In the rapidity direction, this is where the rich physics lies, right? Because you have many sources of fluctuation, starting from the initial state, but also in the final state, they show up and they evolve in the rapidity direction, and they entangle with the physics in the transverse direction. And in the low energy especially, you have a lot of interesting physics that going on due to this rapidity correlations, like the fluctuation of the longitudinal flow, the charge transport, and net baryon transport. This is a very important physics in order to, we need to control in order to really be able to reliably extract, for example, stuff related to the phase diagram, right? So some of this measurement has started, and for example, this baryon rapidity correlation from STAR shows very interesting pattern in the short range, which so far is not explained by the model. And this will be something one should further explore. But on the other hand, here's something I want to argue is that the rapidity scan at the fixed energy is almost like beam energy scan, but within the same event, okay? Because as you change the rapidity, you actually changing the temperature and the mu b. The properties, you may argue, is similar. So you're actually scanning in the same energy, but changing rapidity, you scan this range. But what is different is that you actually have very different dynamics, right? So the dynamics in the forward rapidity is different from the dynamics at mid rapidity. And this provides a handle, right? So you can think this, right? You can, if you have a produced matter at a different rapidity, they corresponding to different positions in the phase diagram. But what's important is that the physics, for example, the fluctuation physics, right, in this different rapidity are not independent from the physics of other rapidity because there are transport between them. So if you can, if we can really have the ability to do this rapidity scan, we will not only understand this, final state physics, but we can also understand the initial state physics, which is super important, right, in order to constrain our understanding. So more information, especially flow fluctuations, if you can do this in different rapidities, will provide deep insight on the dynamics and improve our modeling. Here's one plot I shamelessly steal from Shen Chuan, who is going to give the talk next week. I hope he's not going to hate me for this, but let me just show this very nice plot he showed prior to quark matter. So this is the phase diagram covered by mid rapidity at 200 GeV, 19.6, and 5 GeV. You can see, of course, they cover quite a large region, and you can actually scan this phase space in the T-mu plane. But if you look at the fixed energy and at different rapidity, you actually can see, as you move to the forward rapidity, you're actually also scanning the phase diagram. But the good thing is that you actually can also, by correlating between different rapidities, you also can constrain the dynamics, right? Which is super important. Without that, you will not be able to fully understand this result. But my last slide.
Can you try to come to a close?
Yeah, I'm done. So, I mean, I know there's not much existing capability for doing this, but maybe in the future, with a future detector upgrade, for example, the star forward upgrade with some PT and maybe some PID information, we can do some of this. The ITPC already allows us to do some of this. And the Atlas CMS have this forward upgrade with provide some PID capabilities as well. But at least they are proposing this new detector beyond the 2030 with a PID and the eta large rapidity coverage. But what we really need is that with this new detector, maybe we should go to lower beam energy and explore the rapidity correlations. And I think this will be a dream detector that one can do this kind of physics. So let me go to my summary. I discussed, I argue that the flow and hydrodynamics are the most important tools so far for us to really understand the dynamics and the properties of heavy-ion collisions, which are the baselines for other studies, including the critical endpoint search. But we have a list of key challenges. The question is how to disentangle different stages, right? You have many different phase sources of fluctuations which need to be disentangled. My comment is that we need to achieve a precision at the high energy to really improve the baseline for the modeling of a more complex physics at the lower energy. I discuss some future opportunities as well. I think we need to really explore new observables and new approaches to pinpoint the initial state, especially at the low energy collisions. We should pursue, I would say, in my opinion, pursue this collision energy collision system scan, which only RIC can do comprehensively and easily to really constrain our understanding of initial geometry and the initial flow. And rapidity scan is will provide another handle on the phase diagram and also very importantly, the longitudinal dynamics. That's all. Thank you for your patience.